everyone. I think we can start with today's lunch colloquia. We have the pleasure to have Dr. Angelo Caregnato-Neto that is presenting today, and he is visiting Tamas, and he is here since October, and he will be here as a visiting until September, and is looking forward to ideas and collaboration on the new topic that he is studying over here. And without further ado, I leave the floor to Angelo, that he is going to present mixed integer methods for robotics.
Thank you very much for your presence. And just start thanking Carlo and Thomas for the possibility of being here and presenting myself to the group, presenting my work as well. So I'm going to talk a bit about mixed integer methods for robotics, with particular emphasis to motion planning and a bit of decision making, but the problem is so difficult that I will pretty much constrain myself to motion planning. So basically, to start, I just want to say who am I? I did my master's at ITA, Aeronautics Institute of Technology in Brazil, on the subject of helicopter flight planning and control. I did my PhD also at ITA on the subject of multi-robot motion planning and decision making. And I did work with Embraer, which is a Brazilian aircraft manufacturer, on this problem of drone swarm, research on drone swarms as well. Also, during my PhD, I've been here at TU Delft already. This is my second time, my second visit. And now I'm doing my postdoc at the University of Campinas, and I'm visiting the supervision of Professor Tomasz Kowicki. And the subject is distributed mixed integer programming, applied to autonomous driving, but I will talk about autonomous driving. I'll talk generally about robotics. Okay, so the outline of this presentation is a very quick introduction to multi-robot systems. Then an introduction to mixed integer programming, some examples, how to handle complexity, dimensionality, my ongoing work, and some final remarks. So start with an introduction to multi-robot systems. So why do multi-robot systems matter? They matter because it's not hard to see that integrating a robot into a group of robots and make them work harmoniously can enhance their efficiency, flexibility. But I think the spirit of multi-robot systems is this idea of you taking out the complexity of individual robots and put it into the algorithms that control their collective intelligence. So you can make a very simple robot do some very complex tasks if you integrate them with a bunch of other robots. But the example that I like to give is the example of syncing or disabling an aircraft carrier, which is a very complex task, right? And you can go about it by building your own aircraft carrier. You can go about it by building a fleet of submarines and other ships. But nowadays, you can think about building a swarm of quadcopters, for example, which is a very, very basic type of robot. And the idea is that by building this swarm, you can leverage the sheer numbers plus some kind of collective intelligence that doesn't have to be very sophisticated. And by leveraging this, you can complete a very, very difficult task of syncing an aircraft carrier. So this, to me, is the spirit of multi-robot systems, is the idea that you can take something very simple like a quadcopter and use it to do something very complicated. Okay, I will talk a lot about applications. There are a bunch of them, you can imagine. I just want to make a point in robotics that it's typically said that humanoid robots are the generalist type of robot because they have hands, right? They can use multiple tools. But I think there's a good point to be made that multi-robot systems, since they can handle a bunch of tools individually, they are also generalist robots. So the humanoid robots are not the only generalist ones. So these are typical problems for multi-robot systems. So collision avoidance, avoiding conflicts between the paths given their objectives, task allocation. So you have a bunch of tasks or subtasks. You want to allocate them optimally. And then you have also connective maintenance of local networks, which is very important in some kinds of multi-robot systems. So these are main problems that we have to handle when you develop a multi-robot system, and they do not are typical when you handle a single robot. So the bridge to mixed integer programming is the problem that in robotics in general, not just multi-robotics, you have to solve these discrete decisions, like, for example, to connect or not to connect, to which task should each robot perform. And these are typically modeled as discrete decisions. But there are other aspects that also can be cast as discrete decisions that are not naturally discrete decisions, like how to avoid a collision. You can try to avoid a collision by partially by deciding on a discrete decision of going up, down, left, or right. And also, you have to jointly define variables that are continuous, like positions, velocities, acceleration, orientations of the robots. So this is the challenge. You have to solve for things that are continuous, decision variables that are continuous, and also decision variables that are discrete. And this motivates the study of mixed integer methods. So about mixed integer methods, this is an introduction to mixed integer programming. So what is mixed integer programming? It is, in my view, two things. First is a formalism to write these engineering problems with discrete and continuous variables as an optimization problem in optimization form. And second is the study of how to solve these integer and continuous problems. So this is a general MIP. You have the typical optimization form, a cost and some constraints over a decision variable x. And the only difference here is that x is defined over some integer variables as well, not only continuous, right? And unfortunately, mixed integer programs are proven NP-hard problems, which means that there is very, very, very little hope of finding polynomial time algorithms to solve it. There's a particular subclass of mixed integer programs that are interesting, which is the mixed integer convex program. So the funny thing about mixed integer convex programs is that none of them are convex. They're actually called mixed integer convex programs because they're a class of mixed integer programs that when the integrality constraint is relaxed, the integrality constraint is the constraint that say that a particular variable is an integer. If you relax that, you get a convex problem. So for example, let's say you have a problem with a binary variable, right? It's an integer. If you relax it to be anything between 0 and 1, and your resulting problem is convex, then this is a mixed integer convex problem. So it's a subclass. You have the big class of mixed integer programs with mixed integer nonlinear programming, mixed integer quadratic programming with bilinear terms. And you have mixed integer convex programming with mixed integer linear programming, mixed integer quadratic programming without bilinear terms, and mixed integer second order conic programming. So the point of this subclass is that they're easier to solve, right? These mixed integer linear programs, quadratic programs. And so we're going to focus only on mixed integer linear programming in this presentation. So the good news about mixed integer linear programs is that it's extremely flexible. You can model all of these problems of which robot systems that I mentioned, collision avoidance, task allocation, connective maintenance, and more with mixed integer linear programs. And they can be solved very, very efficiently if you build the model properly. But building the model properly is an art form. And also in robotics, particularly, the good news is that we rarely require global optimal solutions. We can live with feasible solutions very typically. And also one thing that is interesting about mixed integer linear programs that is not exclusive to them, but it's the fact that we actually have optimality gaps. So if we have a suboptimal solution, we can know the quality of the solution in the worst case scenario. Now, the bad news, and there are a lot of bad news, is that mixed integer linear programs, of course, are still NP-hard, and they're highly sensitive to modeling. So I have a history with this. Once I was writing a paper after finishing all of the simulations, and these robots were modeled as squares of length 1 or side 1. And in the middle of writing it, I realized that they had to be 0.8, something like that, for some reason. And I thought, well, the robots are smaller now, it should be easier to solve, right? And then I tried to run it with a smaller robot, with a bunch of smaller robots, which should be an easier motion planning problem. And it took 3 times the time to solve it, which is just to show that it's highly unpredictable what happens. It's not really easy to predict what happens when you change a mixed integer linear program. They're very sensitive to modeling. They can be very hard. You can imagine that since they are so sensitive, they're really hard to compute in real time with a receding horizon strategy. But it's possible. I'll show an example. And one thing that is very sad is that mixed integer linear program solvers do not leverage CPU parallelism. So we cannot benefit a lot from GPUs. So if you have a very powerful GPU, it doesn't really make a lot of difference for mixed integer linear programs. There are people working on this actually, trying to make GPUs somehow help in solving mixed integer linear programs. But so far, I don't know if it's really working very well. So given that this is mixed integer program, I want to quickly show what is a very basic, to me, the most basic constraint that you use for multi-robot systems, which is the collision avoidance constraint. So this is the space of relative positions between two robots. Robot 1, robot 2, this is two positions. It's just a relative position, right? And the idea is pretty simple. This is this square is centered at the origin of this space, and you want to keep the relative positions outside this black square. That's it, right? If it's inside, they're too close together and they are colliding. So what the mixed integer program does is it decides in which side, the green, the red, the magenta or the blue, which side does the relative position of these robots have to be. And you can write this as some constraints, it's very easy. But although it's easy, the number of constraints that you need for a multi-robot problem and the number of binary variables that you need for this model scales quadratically with the number of robots. So this is pretty bad. And in the worst case, the branching bound, which is the state-of-art type of solver for mixed integer linear programs, it's the worst case runtime is proportional to 2 to the n squared minus nr. This means that you have exponential, then a square term in exponential. This is really bad. In practice, this is just the worst case scenario, but in practice, it's much faster. But in the worst case scenario, it's really, really difficult to solve these problems. It takes a long time. All right. So given that I gave a lot of bad news, I thought I would give some examples of this working. So I have a video. Let's see if this works. All right. So this is some work of my PhD. This is a NPC problem doing decision making, assigning targets, collision avoidance, and connectivity, robust connectivity maintenance in real time with MPC running. You have two optional targets, a mandatory one. And this assignment of targets is made online. In this situation, all targets are visited. This is the network. Then you have a second one that is a bit more complex, but not too much. So here are 5 targets. What you see is that they decide online not to visit 2 of them. They decide to visit 3 of them. All of this assignment of all of this planning and connectivity maintenance is done online, right? So this is a model with more than 1,500 binaries that we managed to solve in less than 1 second. There is this one as well. This is open loop planning only. So this is a bit difficult to explain the technology that requires this kind of connection between robots. But you have a base, 2 relays, and a leader. The leader has to visit target 1 and target 2, and the relays have to connect base to leader at all times. And the way that they connect is through these beams of blue light. But this is quite complicated thing to solve. And we didn't find any solutions, and we managed to solve it with mixed integer programming. So these are turtle bots in the gazebo environment. So the leader visits these green squares, and it keeps some kind of connection. You can see here with the base, with the projection of these beams of light. Correct. And last I want to give is just what I did here at TU Delft last time that I've been here. I worked with Professor Luciano Siebert and Arkadis Donikov. And basically the idea was we wanted to take off 1 robot out of the problem and insert a human, just that. And the idea was to try to train a neural network to replicate what the human would do and use it as a prediction model within the MTC framework. And we did that with ARIRL, Advanced Adversarial Reinforcement Learning. And we integrate that with MPC, with mixed integer programming. What we observed that it worked very well, although it was very simple, it worked very well. And we actually observed coordination without no collisions, but also a good task assignment coordination, such that the robots would always help this human and not ever compete with him. All right, so I'm going to talk about handling complexity and dimensionality, but don't get your hopes up because there is not a good solution yet for this, I think. So the first thing I was looking into was distributed optimization theory. So there's very nice results on dual and primal decomposition. For example, this paper from 2016. And it's really, really good. But there is one problem, which is that the number of subsystems of this mixed integer program has to be much bigger than the coupling constraints, the number of coupling constraints. So that means for us that the number of robots has to be much bigger than the number of coupling constraints. And what I show you is that the number of coupling constraints in the collision avoidance problem scales quadratically with the number of robots. So it's the opposite of what is required. So we cannot use these results, although they're very, very strong. So there's ADMM, ADDMM, ADMM. I think it's spelled there. But the ADMM is, as far as I'm concerned, I'm not a specialist on this, but as far as I'm concerned, it's designed for convex problems. So people try to apply it to mixed integer convex problems and try to get some results, but there are no real conclusive theory on this as far as I'm concerned. There are also these distributed planes, cutting planes algorithm, which looked very interesting. I looked at that very deeply, but it turns out that there's a problem of requiring a common cost among all robots, which is not good because we want to minimize energy of robot 1 and robot 2 separately. But also by the division of the authors, it scales poorly, so it doesn't really solve our problem of dimensionality. There's also machine learning, which I think is the most exciting for most people, right? And the idea of machine learning is just to grab this neural network and determine the binaries, the integers with the neural network. And then you inform the integers to the mixed integer linear program, and then this mixed integer linear program becomes a linear program. So the appeal is that inference of a neural network is usually polynomial in time, and also solving a linear program is polynomial in time. So we have 2 polynomial times to solve a mixed integer program. That's great. So that's the motivation behind it. And there's not a lot of work done specifically applying these to multi-robot systems. So there's a gap if you're interested. So there's, as far as I know, there are 2 ways of handling this. There is reinforcement learning. So you can, the good thing about using reinforcement learning is that you can train this network that defines the binaries by interacting with this simulated world, which means that the network is always outputting the integers. And that means that you don't have to solve a mixed integer linear program. You just solve linear programs that are convex. It can be very quick to train. And there are results from a colleague of ours that is doing his PhD here, Kai, where he showed that you can get 20x improvement in max computational times, which is expected. But also this technique cannot handle large-scale mixed integer linear programs, unfortunately. And there's also supervised learning. So the idea of supervised learning is that you have this data set of demonstrations of how these binaries are computed. And these are actually usually constructed by solving mixed integer linear programs. And this is exactly the problem. So if you have a problem with 10 robots, you can use mixed integer linear program to generate these data sets, train your neural network. That's great. But if you have a problem with 1,000 robots, how do you generate the data sets, right? So that's a problem that is being handled by something called transfer learning, which is the idea that you can train your network on a data set with 10 robots, apply the results to 1,000 robots, but still early days for this, I think. Okay, and very quickly, I'll talk about convexification, graphs of convex sets. These are other lines of that are very interesting right now, but I don't have time to talk very deeply about. So the idea is to convexify partially the problem to reduce or completely remove the number of binaries. So one way of doing this is that you get the free space that a robot can operate. You break it into convex sets. These convex sets are the union of the free space. And then you try to decide with the binaries in which one of these convex sets your robot will stay at each time step. And they can show that it reduces drastically the number of binaries if you have a high density obstacle field. And out of these actually came this formalism called graphs of convex sets, which I don't have time to explain very deeply, but it's a very interesting idea that you solve this mixed integer optimization over graphs. Each graph is a convex set, basically. So it's an interesting thing. I have to read a bit more about it to see how powerful it is, but it is quite popular right now as well. So if you're interested, there are very nice tutorials on this from Professor Tobia Marcucci and Russ Tedrick. And there's also very simple early attempts where you just clusterize and sequential solve. So basically, you break these big groups of robots in small clusters, and then you solve for the first robots, then you use the solution of first robot to solve for the second robot, etc. This was the work done in 20 years ago, basically, but it's still very interesting. So my to finish, talk a bit about my ongoing work here at TU Delft, also with some students. So the things I've been interested in this year are air-ground collaborative localization. So I don't have time to explain exactly this, but basically you want to plan trajectories for a quadcopter and a bunch of ground robots, such that the robots always stay in the field of view of a camera that is attached to this quadcopter. This is a very interesting problem because the field of view changes with the height of the quadcopter, right? So there has to be some very interesting coordination there. We also have this problem of multi-robot pursuers. These two problems are with some master students right now. And the idea here is to try to push this evader to a capture region. And the point here is that it's very difficult to predict what the evader will do, right? The higher level planning. But sometimes they are running under very simplistic repulsion control laws for collision avoidance. So the idea is try to leverage these repulsion control laws to force it towards the capture region with this coordination of robots. I'm also working on some other network connectivity conditions with Paul there, and artificial reference formulations to fix the problem of high horizons, which is also very bad for mixed programs. Long horizons, not high horizons. So the last thing I want to talk about is just this decentralized method that I've been working with Professor Tomás, which is based on cut generation and decentralization. So the idea basically is that we start with a bunch of local mixed interlinear programs, each one for one robot. And these are supposed to be very simple because they're local. You only solve for local variables. So variables of robot 1, robot 2, and they do not scale too much. So we can handle this. So we solve it separately. They plan trajectories. They can collide in these trajectories, right? Because they're local. And then you detect conflicts in this centralized node. With this conflict detection, you try to build a coupling constraint. So it's a coupling constraint, for example, to avoid collision. And it's a weaker coupling constraint because the idea is that it has to be decomposed into local constraints afterwards. So it cannot be the original collision avoidance constraints. They cannot be decomposed. So they're weaker in the sense that they perhaps do not guarantee that there is a collision, but eventually they hopefully will guarantee it. So to give a concrete example very quickly, here you have two robots and a collision time step 3. So you have here the relative positions. And here is conflict detection. You see the relative positions within this square. So there is a collision. And this is the space of relative positions. So the idea is to generate a cut, which is this line here, this dashed green line. And the idea is to push it towards this vertex such that you cut off the solution, such that when you solve the next optimization problem, it cannot find this solution anymore, right? It's out of the feasibility space. So this is a very, very old idea from the 50s, but I'm trying to apply it to some collision avoidance problems. So the idea is try to maximize this cut such that it tries to reach this vertex here, because if it reaches this vertex, then you have a guaranteed collision-free trajectory, because your relative position is outside necessarily the square, right? Now, this is the coupled constraint over the relative position space. The idea and the challenge is to make a decomposed constraint over the position space for each one of these two robots. So this is their positions, and this is the relative position. The idea is to build cuts for each one of the robots. And it's not hard to see that if you have a solution in this faded red line, faded red area, or blue faded area, this vector, this magenta vector stretches, it increases length, and then you increase length of these two. So these are two, this is a sufficient condition for that. And the idea also is to maximize both of them such that you can try to push the relative position outside the square. Now you may be asking, why don't we just impose this directly? And it's because it's difficult to say how much of each robot will give of contribution to pushing the relative position outside, right? You can have, for example, you can divide the contribution by 2. So both of them have to put their positions on these sides of these lines, but perhaps it's unfeasible, right, for one of the robots. So you don't really want to impose such a conservative constraint. So the way it works is just you run your algorithm, you get these constraints, you solve your local mixed integer program again, and then you see if there is any conflict. If there is a conflict again, you run it again. If there's no conflict, you're fine. And what I can show right now is that I can build cuts that maintain feasibility, and the algorithm eventually resolves all conflicts. What I can show is that the robot reached their objectives. So they can solve the problems, but perhaps they will stay. Yeah, so final remarks. So if I can help with anything, or if you saw something in here that you think you can help me, please let me know. Feel free to contact. I'm here at TU Delft until the end of September, and you can find me in the guest room in the first floor, in the end of the hall. Or you can send me an email at this address. Thank you very much for your attention.
Is there any question?
So I have thanks for your presentation. It was very nice and very interesting simulation to implement the actual. I have a question about curiosity in general. So when you're planning using mixed integer, any type of methods that we use some relaxations, and we have safety critical issues. So yeah, at the end of the day, we have some approximate solutions. Because of this relaxation and branch and if you stop varying the branch and one and branch and call, you have an approximate solution. What will happen to safety? It's very general question.
If you get the suboptimal solution out of early termination,
Yeah.
If it's a suboptimal solution, it's a feasible one, presumably, right? So you have to write your constraints such that you have robustness, right? So you write a robust constraint. If you get a feasible solution, presumably you are safe.
Thank you for the presentation. It was interesting. So at some point in slide number 24, you have shown it that people use also neural networks or machine learning methods to generate these constraints and then generate the integer
variables.
And then the MILP becomes an LP.
Sorry?
MILP becomes an LP.
Yes, exactly.
Yeah.
Exactly.
So my question here is that how do you ensure the feasibility of the problems in such cases? So suppose that it generates some sequence of binary variables such that the problem is itself infeasible, and you keep on doing it loop and loop. I don't know. So is there any such work which gives a guarantee, or no? It's just some heuristic.
I think it's probably fundamentally impossible to guarantee. Because I think this problem, if you guaranteed it, perhaps it would become a polynomial algorithm, polynomial time algorithm, and I don't think this is allowed. But to be more concrete with your question, no, there's no guarantee. Sometimes if you have a feasibility rate, let's say, it can be very good. For example, the work from Kyle, he showed that reinforcement learning has a feasibility rate much better. So you have to have some kind of safety algorithm that will check if it's unsafe, we have to use another type of solution, another type of algorithm.
And the same question is for your work, last one that you have shown, that you have this constraint generator and then so you also have the same problem, right? Because you may end up with the feasibility issue.
Yeah. But my point from doing this is that there's more hope that we can show that we can eventually converge to a feasible solution than with machine learning. It's very difficult to show with machine learning, but with this, it's more, I guess it's more simplistic, right? It's more mathematically handleable. So perhaps you can show eventually that with enough iterations, you get a feasible solution. This is the argument for it, I guess.
Yes.
Thanks for the presentation. Really nice. I'm curious about the standard, say, MIP NPC. So in your examples, all the time, even though they're using some kind of, I suppose, some rolling horizon, they manage to get to the final destination. I'm wondering, like, if you put them in a maze, and then it really needs the foresight, in my mind, like, to reach the final destination. Do you still, like, what are the conditions or the guarantees that you can get that still with a receding horizon scheme, you manage to solve a complex, like inherently far-sighted?
Yeah, that's a good question. It's a problem, really, because there are formulations that can guarantee that. But the problem is that you have to have a very long horizon, and that makes the problem extremely complex. It increases the complexity of the problem. So if it's large enough, you can navigate the maze, and it will find some solution, presumably. What we are working on, and there's some works on, is this idea of and reaching this objective is a hard constraint, right? So it has to be reached.
Yeah.
So we are working on problems where this is not a hard constraint in mixed integer program. So it's even if you can't reach it, you eventually recede the horizon towards that direction, and eventually you get there. And it doesn't get unfeasible because in one planning round, you don't get there, you get to an artificial reference that eventually will get there. So this is the kind of methodology that we're trying to are working as well to try to avoid the necessity for a maze, for example, is a good example where you have to have a very large horizon to get to the objective.
Great. So if there is no other question, we
Yeah, a quick question, because you brought up the artificial reference. So do you have plans about how you're going to construct this artificial reference?
Yes, it's a bit difficult to explain.
Okay, yeah.
But I already started working on some formulations for that. But then, it's very difficult to explain without some kind of illustration. But
is it related to any previous work?
yeah, it's really inspired by the artificial reference methods that we have for tracking MPC. It's very similar, but the difference there, I think, is that in the spirit of mixed integer programming, you have to have some kind of guarantee of reaching the target in infinite time, not asymptotically. And this is a bit tricky, but it's in the spirit of the method. So we're trying to figure out if there is a way of doing this.
Yeah. I think there's work from Johannes Kohler about this.
I don't know.
Okay. Yeah, okay, then we should talk about it.
Oh, okay, great.
Yeah,
Great.
Send you the paper, so we know.
Yeah.
Oh, okay. I didn't read it yet. Sorry.
any other question?
Just a quick. But in I think in slide 40, I don't know. So you have a local mixed integer. Oh, the next is. Oh yeah, local mixed integer. I just want to. I'm curious how you solve this local mixed integer. Just you use existing solvers to solve this, or you use some method that you develop?
Well, it really depends. On practice, it's not that easy to embed, like Grob is a state-of-art solver. It's not that easy to embed it in a little robot, for example. So perhaps you have to devise your own algorithm to solve it, your own branching bound designed specifically for this problem. But generally, you can use some kind of commercial solver to solve it.
Yeah. I'm curious about the algorithm. You use branch and bound here, or you use.
Mainly it's branching bound, but Grob uses a bunch of things simultaneously, like cutting planes algorithms, then branching bound, and a lot of heuristics. But yeah, the main horse there is branching.
And have you thinking about so you can write the binary variable simply as for example, if x is a binary variable 0 or 1, you can write it as a x multiplied by 1 minus 6 equal to 0.
X
multiplied by 1 minus 6 equal to 0. You
Okay.
can replace this instead of, and you can, no, you have a non-convex problem. I just want to know, have you thinking about, for example, non-convex algorithm?
No,
Okay.
I am ignorant about that, actually. Haven't been thinking about it.
Thanks.
Do you have any suggestions about non-convex algorithms, by the way? Or maybe some path there?
No, I just curious that,
Okay.
I mean, have you thought about it, kind of?
Okay.
Okay. Any other question? If no, then we can thank the